So I'm going to ask you to digress your memory to switch to high school math and physics a little bit. My name is Hongrui Jiang. I'm a professor at Electrical and Computer Engineering, so affiliated with the Biomedical Engineering and Material Science program at University of Wisconsin-Madison. My talk is about accommodative contact lens for presbyopic correction. I'm going to talk briefly about the motivation of this work and talking about different challenges and the different aspects of the whole project of how to make this thing. And finally, I'll give the summary and acknowledgement. So motivation. We all know that the presbyopia is a common public health issue. No matter how healthy you are, no matter how lucky you are, at some time down to 60 years of 50, 60, you're going to get that. And you simply cannot avoid it. It's the most common ocular affliction that is affecting the daily life of people around the world. It was estimated that back in 2005, there are more than 1 billion patients globally. And it's basically because of as you're getting older, the ciliary muscle starts to lose power, and you're getting harder and harder to be able to see things closer. It's not an old issue, and there are many treatments to deal with it, but the current treatments all have drawbacks. One category of the treatment is glasses, using glasses or contact lenses. They have a loss of stereopsis, and it requires patient adaptation. So towards the end, okay, so we all are very familiar with this type of the reading glasses. It's basically you have to switch gears, you have to put the glasses down and put on the reading glasses. That's obviously not very convenient. And there are bifocals and the multifocal glasses, essentially breaking the whole glass area into different zones to be able to focus onto different range, distance. And that requires a lot of patient adaptation. And I can attest to that because I just get onto my bifocal a couple of months ago, and it took me quite a bit of time to get used to that, to start to do this. You can also do contact lenses these days. The idea is very similar, is to break into the contact lens into different zones to be able to focus on different areas. And because you're losing the total area of the zone, dividing the area of the lens into different zones, you are actually lower the sensitivity, photosensitivity of the lens itself, which means that at night it's going to be harder for you to see, simply because you have smaller areas. Effectively, you are reducing the size of the aperture that intakes the light. You also, of course, have the option of surgery, but the surgery has a loss of contrast, sensitivity, and also suffers the difficulty in night vision. And at the end, of course, there's always inconvenience. So people have tried to do accommodation using a contact lens. And one big advantage of a contact lens versus the reading glasses or glasses is that I can stare at you, but I still roll my eyes to see different areas. While you wear glasses, everybody will know where you are actually looking at. So people have been thinking about all these ideas as well, and are trying to get this accommodation into the lenses or glasses to correct presbyopia. Here I have a couple of examples on the glasses side by TrueFocal and the SuperFocus. The essential idea is actually very, very simple, is that you have some kind of a mechanics where the patient or the wearer of the glasses can adjust the focal length by switching the a mechanical structure or turning the knob. This, of course, is very interesting because if suppose when you're driving and you want to read your GPS, you probably don't want to do this and take your hands off the wheel. So there has also been ideas that propose to do accommodative and with autonomous operation. And here's an example that was published back in 2006. It's based on liquid crystal glasses, where they have the sensors so that the focal length of the glasses can be automatically adjusted depending on the distance of the objects between the objects and the patient. But then, of course, the whole thing weighs about 1 pound, which means that it's more like a goggle rather than a pair of glasses. So again, these common old issues comes up, which is inconvenience, device weight, and the power consumption. Here's our solution. We try to develop a accommodative contact lens coined ACLs. So such an ACL would require a diverse array of functional components to fulfill all the requirements that we have. For example, we need to have variable focused lens systems integrated right into the contact lens so that we can adjust the focus. We need to have a power supply to be able to provide the energy, the electricity that is required by the tuning of the lenses as well as the electronic control circuits. And that power supply should have very limited size, and given the size of the contact lens, the power provided is going to be quite limited, which in turn requires that electronics needs to be low power electronics as well. And finally, we all know that the contact lens is soft, flexible, so all the electronics needs to be embedded in the contact lens, and that these electronics need to be flexible as well, while also maintaining its functionalities. So this is the diagram showing that the schematic of our proposed idea. So it's basically, we are going to have all the different components onto it towards the center. This is a tunable liquid lens that is coupled with the pupil crystalline lens. And we have electronics. We have the infrared sensors to calculate the distance between the lens and the object, and energy harvesting modules, and as well as the storage modules. So this is a cross-section of the whole thing. So it's basically everything should be embedded into the whole contact lens structures, which is about 250 microns or 0.25 millimeters. So it is very challenging. And as you can see here, we have 3 pillars supporting technologies to address that. Unfortunately, none are mature yet, but we are trying to address these things one by one. And I'm glad to report some progress we have made throughout the years in this venue. Okay, so the first topic is the variable focus lens. We all know that the lenses and the cameras are widely used in industry, in biomedical applications, in consumer products. So here are some examples. But the challenge, of course, is to, as I mentioned, is to put into the contact lens. So we need to look at what are the emerging variable focus lens technologies. There are basically 2 ways to change the focal length. One is to change the shape of the lens. One is to change the refractive index of the lens material. As a consequence, there are basically a few ways. For example, you can use hydrogel to drive a liquid interface to form a tunable lens. Or you can mechanically actuate the polymer film, much like the true focal glasses that we just saw. Or you can use electric field to reorientate liquid crystal polymers, molecules. So this is very much like the operation mechanism of the displays. But all these technologies have their drawbacks. For example, the hydrogels tends to have very low speed of operation, and the liquid crystal, as well as the mechanical structures, tends to have a much higher power consumption, as well as very complicated controls, feedback that we needed to focus onto the objects. So we developed 2 technologies for the variable focus lens. One is based on electrical wetting, and the other one is based on dielectric force. The first one is electrical wetting. I'm going to talk very briefly about the mechanism of electrical wetting. So essentially, electrical wetting is using electric field to tune the wettability of the liquid onto a solid. And we know that based on the Yang equation, when you have a different contact between different materials, solid, gas phase, and the liquid. And if you have this surface tension varying based on a certain condition, then as a result, you can tune the contact angle, and that contact angle in turn will determine the curvature of the liquid droplet. So if you have a mechanism to tune or adjust the contact angle, you have a tunable lens. Electrowetting is based on that idea. So essentially, we can use electric field at the interface between the solid and the liquid to change the contact angle, thus the focal length. And this is actually somewhat similar to, not exactly the same, but similar to the idea in in the biological world. For example, we're very familiar with all these beads, water beads flowing down the lotus leaf, and that's the wettability that's playing the role. Okay, so what we are doing is electrowetting. Electrowetting was initially invented on metal surface, but we are doing dielectric, which has better control and less breakdown voltage. So we're doing electrowetting on dielectric called EWAD. So this diagram shows the basic idea. So basically, if you have one pair of electrodes and exerting electric field on the interface, you will be able to change the contact lens. As I said, the shape of the droplet will be changed, hence the focal length. It can offer very wide focal range. The response time is pretty fast, on the range of 20 to 15 milliseconds, good enough for most applications. It consumes very low power. The reason is the changing. The power is consumed only when you change the status. When you maintain the state, it doesn't consume any static power anymore. It's a robust system, but the downside is that normally everything is made of rigid materials, for instance, glass. So we have to, as I will show later, we have to do a lot of basically reinvent the whole thing to make this thing onto flexible polymers and potentially into the contact lens. So this equation describes the optical power as a function of the voltage applied. Here's the diagram of our structure. So what we have realized right now is that we are able to make liquid lens based on the electrowetting mechanism onto a PDMS, flexible polymer substrate. And this PDMS can in turn be wrapped onto any curved surface. So we do have the flexible structure already. The structure is made of 2 layers of soft polymers, and they're both made of PDMS. One is thicker, one is thinner. And the aperture of the lens that we have realized is on a range of 4 millimeters, and that number is selected to match the size of the pupil. At this moment, we are able to put it onto a contact lens, and ultimately, of course, the goal is to make this embedded into the contact lens. I guess I won't go into the details about how these things are fabricated. As I said, we took advantage of the semiconductor fabrication processes, but we have pretty much reinvented the whole procedures because we're dealing with subpolymers, we're dealing with low temperature materials, and so it's very different than traditional and conventional semiconductor integrated circuits fabrication. So ultimately, here's the device that we have been able to realize. Some characterization of the lens. As we can see here, we are able to make the lens change the focus from diverging to converging, and using the United States Air Force resolution chart, the best resolution we can get is about 25 line pairs per millimeter. It's not superb yet, but it's pretty good in terms of a micro lens, and of course there's a room to improve. And the focal length is between the minus 15 millimeter to 28 millimeters. So roughly enough for most of the applications of the accommodative contact lens that we're talking about. But the first generation device has some drawbacks. For example, it's really hard to determine the sidewall distortion, and in turn, in terms of determining the shape of the lens and then the aberration. And it's fairly difficult to pattern the electrode or the hydrophobic coating onto the side walls. So we have come up with a second generation design, which actually uses the flat functional layers, which is shown in this diagram. So it's basically, if we change the shape of the layer itself, the curvature of the droplet will change accordingly as well. With this method, we can put the whole droplet onto a flat surface, relatively flat surface, instead of having to take advantage to use the vertical side walls. And we also changed the materials as well. For example, we promoted the adhesion of PDMS and using the aluminum electrode rather than the ITO that is commonly used. And we use the Parylene C. The Parylene C turns out that it provides a lot of advantages. It has a low permittivity to the moisture and the gases, and so that's solving the PDMS porosity problem. It has better optical transparency. It's pinhole-free, and it's pretty inert to chemical and biological samples. And as you can see here, we're able to make these optical structures, including the interconnects and metal lines, onto all kinds of different curved surfaces. This is, for instance, this is a goggle, so it's a curved surface. This is a simple rod wrapped onto a rod, and this is on the Parylene C substrate film itself. Okay, the fabrication process needs to be adjusted, of course, accordingly. But essentially, it's based on the Parylene C and the PDMS coating. If you're interested in the details, of course, we can talk about it during the lunch break. So I have more experimental results for the second generation devices. We are able to lower the driving voltage of this a little bit more. You don't be too shocked about the high voltage right over here, because ultimately the devices will be sealed. And we're talking about the static voltage at a very short distance, so the total voltage is actually going to be lower. And again, we'll be able to change the radius of curvature of the lens, thus the focal length. So the focal length range is from 38 to 29 millimeter. So that was electric wetting based. Now I switch gears to the dielectric force based. So we're exploring two basically revenues to see ultimately which one actually is going to be the winner. Dielectric force-based lenses, the idea is similar. So it's basically you have an array of electrodes, and you create the gradients in the electric field, and the electric field will exert dielectric force onto the liquid. And because of the gradient in the electric field, there is unbalanced or asymmetric dielectric force, which in turn will drag the liquid, either spread it out or push it up. And with that mechanism, we can have a tunable lens as well. So here's an example of an oil droplet which serves as the lens using this mechanism. So here's the pictures showing the performance of the lens. It's basically we have the ring electrodes. We use the ring electrodes to maintain the circular shape of the lens to reduce the aberration. And at different voltages, the contact angle of the droplet changes, and the shape and the size of the droplet actually changes as well. And thus, we are changing the focal length of the lens, which is shown right over here. And these lenses are able to focus objects. As you can see here, the size of the images of the same objects changes as we tune the focal length. And the resolution right now is about 18 line pairs per millimeter. Okay, so I've discussed about the first technology pillar. Now I'm moving towards the second one, which is the power supply. Our idea is to perform energy harvesting through solar cells. Specifically, we're interested in using dye-sensitized solar cells. And we're also interested in integrating the storage capability onto the same device as well. The motivation is very simple, because when you drive through the tunnel, you want your lens still work. So we really want the dual functions in one single device. This turns out to be quite a bit of a challenge. In recent years, people are interested in something so-called the photovoltaically self-charging cells. So basically, you try to combine the function of the solar cells as well as the storage. The challenge comes from in the conventional solar cells, we all know that when the light is removed, then solar cells stops working. The reason is because of recombination. Once you generate electron-hole pairs for the electricity, but when the light goes off, the electron-hole pairs will recombine. So our idea is that we came up with the idea that theoretically, if you have an ideal interface, and you use that interface to block the recombination of the hole and electrons, or at least to prolong the whole process, then you can prolong the holding of the electricity, and that holding can be used, in turn, can be used for storage. And that is the idea behind this work. So what we do is that we functionalize the Dyson-sized solar cells, the counter electrodes, using a very high dielectric constant polymer in combination with the zinc oxide nanocomposite. So basically, it's right over here. So this high dielectric constant materials forms a thin layer, essentially forming a capacitor. So when the light is present, they will charge this capacitor, and when the light goes off, this capacitor itself will hold the charge unless you ask it to discharge it to drive the circuit. And so that's the basic idea of it, and we made a device. I won't go into details about it. The key is that choosing this right high dielectric constant materials as the capacitance material, as well as the zinc oxide nanowire array. And this array turns out to be very important because we want to increase the total surface areas. The higher the surface areas, the higher the capacity of the whole structure. So here's the electrochemical characterization. So basically, we form these two electrode photovoltaically self-charged cells. And on the left, it shows a very typical performance of a Dyson-sized solar cells. This is the voltage versus the current density, typical performance for a solar cell. But what is more interesting is probably right here, is that this thing has as you can see here, after the onset of discharge, it takes a certain amount of time, quite a bit of time, 15 minutes, to discharge this, which shows clearly that the capacitive effect of the PVDF/zinc oxide is working. So which means that the charge is actually stored right onto the chip, right into the device of Dyson-sized solar cells. So that is very promising. So we are able to realize 3.7% of efficiency, which is the photo to electric conversion efficiency. That's pretty high for Dyson-sized solar cells already. At the same time, we're able to demonstrate energy storage of 2.14 coulomb per gram. So that's pretty promising as well. And the whole process potentially can be fabricated using a flexible substrate for the contact lens. A little bit more characterization about the performance of the PVDF versus the zinc oxide. Again, I won't go into too much details. It's basically the thickness of the PVDF, the composition of the zinc oxide nanowires, all has some effect onto the charging and efficiency. And I'm going to wrap up my talk by having on this one slide. If you recall that the third pillar technology is actually integration of everything into the contact lens. And we're going to have electronics in it. So we need to have somehow be able to have the electronics fabricated within a flexible, soft substrate, a material such as contact lens. So we need to come up with a strategy of integrating of all these things. And so this slide shows the general idea of it. It's a different project, but it shows the general idea of it. So basically, the idea is that, okay, we're going to take advantage of the semiconductor industry fabrication technology. We're going to make the electronics on traditional materials, like, for instance, silicon. But the key is we're not going to make them continuous. We're going to break them apart into small islands. And these small islands will be connected with flexible interconnects that conduct electricity. Think of it as a fishnet. Okay, where the knots are the electronic components, while the threads are the interconnect. So this fishnet, of course, becomes much more flexible, and you can basically wrap this fishnet onto pretty much any kinds of a surface. So that is the general idea. So we make the electronics, everything, onto a flat surface, and we match it with a curved surface, for example, the contact lens. We wrap it around it, and that will maintain the flexibility as well as the operation, the electronic operation of the whole thing. Okay, so I'll give the summary right here. So basically, we have proposed a very challenging and interesting idea of realizing accommodative contact lens for the presbyopic correction. And these, we have made some promising progress towards that in terms of making the adaptive lenses on the flexible substrate to realize in situ power supply as well as integration with the flexible electronics. Thank you. And finally, I want to acknowledge the people who are behind working on this, and especially thank the NIH for the New Innovator Award to allow me to pursue this very challenging and ambitious project. And I'll be more than happy to answer questions. Thank you. Okay. If you have questions during the lunch break, we can discuss about it.